Okay, we'll go ahead and get started here. Um, okay, so it's week 7, um, and I'll introduce support vector machines here, and so we'll get started on this topic, and then we'll have the midterm exam on Wednesday, and then I'll wrap this topic up on Friday. So this is we'll take a look at support vector machines. Okay, so support vector machines is a classification method. It's got um, it's got this really cool sounding name, but what it's doing and how it works. I guess is kind of neat. But yeah, I think the name of it just sounds really cool. But what's actually happening, at least with the simplest version, is not terribly impressive. Okay, but I guess the math behind it allows for some creative uses here. Okay, so today I'm going to start off with the simplest version of the support vector machine, and this is known as maximum margin linear SVM. Okay, so what we're doing is we're going to find a linear boundary, and we're going to try to maximize the margin. And this is going to form the basis for which um, we can do kind of more advanced support vector machines. And so, if you hear someone use a support vector machine, they will it will generally not be a linear SVM. It will be kind of what we'll call a kernelized SVM, where they apply this special function. But it's based on it's built as an expansion of kind of this topic of the maximum margin. Okay, and so the maximum margin linear SVM, it only works for data that is linearly separable. Okay, so I will show you a picture of what I mean, and and if you have data that's linearly separable, the idea is you want to find two parallel, what we'll call hyperplanes. Okay, so we're assuming our data exists in high dimensional space, but for illustration, we're just going to look at two-dimensional data. Okay, so we're going to have data in two-dimensional data, and so a hyperplane in 2 dimension is basically just a line. Okay, and what it's going to do is these parallel hyperplanes, or in our case, parallel lines, um, each separate two classes from each other, and then what we want is we want the distance between these lines, the distance between these hyperplanes, to be as wide as possible. That's where we have the maximum margin. Okay, the distance between them is known as the margin, and we want that distance as wide as possible. Okay, and so I'm going to show you some points that are linearly separable, and then we'll look at several possible pairs of hyperplanes. They're going to just be shown as dotted lines, and then the idea is to select the lines that are going to have the maximum margin. Okay, the region between the dotted lines is what we call the margin, and then the solid line in the middle, well, would be the linear SVM boundary. Okay, and then we will settle on, once we find the margin that's the maximum, that will be the maximum margin linear SVM boundary. Okay, okay, so linearly separable means you've got some classes of points. So here I've got these blue dots represented by positive signs, plus signs, and then I've got some red dots represented by minus signs. Okay, and this is linearly separable because we've got I can draw a line somewhere between here and here that would separate the blue from the red. Okay, now if I had a blue dot right here in the middle here, then this problem will no longer be linearly separable, and maximum margin linear SVM would fail. Okay, so this maximum margin idea only works when you have linearly separable points. Okay, so that seems like a huge constraint, and absolutely it is. Okay, because there will rarely be cases where this you have data that is linearly separable in 2 dimensions in the wild. Okay, but for illustration, this is what we have. So we've got some blue dots over here, red dots over here, and they are linearly separable. And what we need to do is we need to draw a line. Okay, we're going to draw parallel hyperplanes. Okay, and it might look like this. Okay, and so if I draw a hyperplane like this, okay, then the farthest that these two lines with this slope can be will go right here, because if I go any farther, then the this point will be inside the margin, and if I go any farther this way, this red dot will be inside the margin. So here are parallel lines that separate the blue from the red. Okay, so this line separates the blue from the red. This one also does, and then the line in the middle is kind of would be the linear boundary. Okay, but obviously if we pick different slopes, so here I'm choosing different slopes, and I'm showing you kind of the widest that the margin can be. So okay, so here are just different options for what parallel hyperplanes can be. All right, and so this seems like a fairly good candidate. Okay, and then here's also another candidate where okay, so you can see at this point I got, this looks like the widest margin. This is a pretty wide margin. I think this one's even wider, and these seem pretty wide, but not as wide as this one. Okay, and then these also count as hyperplanes that separate the blue from the red, but these would not be the maximum margin ones. So the one that we would choose would be the one with the widest margin. Right? Is that okay as far as what we are trying to do here? Okay, so we have these kind of these hyperplanes, and this in this case, this would be our maximum margin boundary. This line in the middle would be the maximum margin linear SVM, okay, because it's a straight line for the linear part. The width of this thing is as wide as possible, so that's the maximum margin. Okay, and again, this is kind of a contrived toy example, but this is the solution that we would choose for drawing a straight line boundary between the blue and the red dots. Okay, so so which hyperplane boundary should we pick? So SVM says we're going to pick the one that maximizes the margin. Margin is defined as the perpendicular distance from the decision boundary to the closest point on either side. So if we go back to this, we're measuring basically the perpendicular distance there. And the closest points to the decision boundary, okay, depend on the boundary that's chosen, and the closest points are called the support vectors, and they will lie on the margin's edges. Okay. Does the distance on both sides have to be equal? Yes. So you will pick basically the line in the middle from, say if you have these parallel hyperplanes, you will pick the line right in the middle between those two parallel hyperplanes. Okay. And so the closest points, they are called support vectors. They will lie on the margin's edges. And they are called support vectors because you can change the location of the other data points, and the location of the boundary will be unaffected as long as those support vectors remain the closest points to the boundary. So let me just kind of go back and illustrate. All right. So these three circled points are the support vectors, and I could technically move any of these blue dots over here to other locations, or these red dots to other locations, as long as I don't go into the margin. Okay, that this will be the boundary. Okay, I don't know if you guys can see that this will stay the boundary even if we move all of these around, because what we're looking for is a pair of hyperplanes that separate the blue and the red. Okay, and you know, with the kind of the widest distance between them, and I won't be able to achieve anything wider as long as these 3 points are part of my data set. Okay, I cannot achieve a wider margin. Okay, so this is it. Okay. So those are the support vectors, and basically, as long as you're not getting data points that are closer to the boundary than the support vectors, the boundary is not going to change. Okay, so it really only depends on those 3 data points. Okay, so how do we? So this purple line indicates the distance that we are going to try to maximize, right? So we're trying to maximize the margin. The margin's the perpendicular distance to the boundary. Okay, this would be a non-optimal boundary, right? And we can see that the distance here is a lot smaller. These would serve as the support vectors on this non-optimal boundary. This is the one that we want. Okay, we want to maximize this margin here. Okay, so mathematically, so visually, that's kind of what it looks like. Okay, you know, trying to do. Sorry, this got kind of messed up, but so visually, this is what it looks like in 2D, and we want to kind of express this mathematically in a way that could work not just in 2D but in higher dimensions as well. And so you know, visually we can kind of do this, but we need some kind of mathematical way to express this. So so this is how we go about doing this. Okay, we're going to say our training data, we've got n data points in the form of x1, y1 all the way through, I'm sorry, this would be x1, t1 all the way up through xn, tn, okay? Where t is the class label. So, sorry. Okay. So these are the class labels. So note that we denote the classes as either +1 or -1. So rather than, you know, like in logistic regression, you often would denote the class labels as 0 or 1. Here we're going to label them either +1 on this side or -1 on this side. Okay, and each of these x vectors is going to be d-dimensional. Okay, and what we're trying to do is we're trying to find this maximum margin SVM that will divide the group of points from where you know, the positive values, the +1s are on one side and the -1s are on the other side, right? So that the distance from the hyperplane and the nearest point from either group is maximized, right? So this is just kind of formally stating what it is that we want to achieve. Okay, we want this distance maximized, and so these are the closest points here. Okay, so any hyperplane can be written as basically the set of points x. Okay, so it is, what is the set of points x, which is the hyperplane, such that some vector w, dotted, when you take the dot product of w and x together, time, plus or minus some constant is equal to 0. Okay, and if you express it like this, w will be a vector that is normal or perpendicular to the hyperplane, and then the hyperplane would be all of the x values that basically align so that this equation is satisfied. All right. Maybe I'll try to illustrate this. Well, I don't know. But so in our in this, we've got x1 and x2, and these would all be hyperplanes, so that basically the hyperplane is all of the x values, x1 and x2, that satisfy w dotted with x equaling some value. Okay, and that can be expressed with kind of the letter b. Okay, so w dotted with x will equal some value here, and that will hold for everything along this line, and it will also be true for everything along this line. Okay, so this is what we have. Okay, w is a vector that's normal or perpendicular to the hyperplane. All right, so the parallel hyperplanes can be described with the equations such that w transpose x minus b is equal to 1 for everything on the positive side of the margin, and w transpose x minus b is equal to -1 for anything on the negative side of the margin. Okay. So so basically, we're just going to try to make sure. So this is going to represent kind of the middle, and then so this is where w transpose x minus b is equal to 0, and then here it's going to be +1, and here it's going to be -1, and technically it could be +1 for any of these things, but we're going to choose it to be +1 and -1 for kind of these boundary points here. Okay, so so I've kind of labeled this just with my pen here. Okay, so we've got all the dots along here will define the hyperplane. Okay, and that's where we're going to have w transpose x plus b is equal to 0. Yeah, if x nu is on this hyperplane itself, it's not going to get classified as plus or minus. Okay, as far as the dots that go on kind of these hyperplanes, though, they will be classified as +1, and dots along this hyperplane will satisfy the equation that w transpose x plus b is equal to -1. Somehow I have a plus. It doesn't matter. It's there. It's just some constant b. Okay. All right. So so this purple vector is the margin. Okay. And what that is the result of projecting. So there's a vector, okay? So some vector x1 minus x2, okay? It could either be this, or it could be technically this vector, okay? So if you just pick one point on this hyperplane and one point on this hyperplane, then the vector that connects them will be x1 minus x2. So if you call this x1 and this is x2, the vector that connects them will be this. And if you project that vector, right, which is what we get when we do a dot product. So if you take the dot product of the vector against basically the direction that points in the margin, then you will get the margin itself. Okay, even if the vector were to be drawn from this dot to this dot, if we project it onto this the direction perpendicular to the to kind of the boundary hyperplane, then you will get the margin, right? So if you recall, kind of dot products between vectors is the projection of one vector onto the other vector. Okay, so we're going to say let x1 and x2 be the closest points from the two classes. Okay, so the vector x1 minus x2 joins the points x1 and x2, and with the way the boundary is defined, w itself is a vector that's going to be perpendicular to the boundary. Okay, and if you do w divided by the norm of w, that's going to be the direction that's perpendicular to the boundary. Okay, and so we arbitrarily just say that gamma is going to be the distance from the center to the margin, and that the total distance of the margin is going to equal 2 gamma. All right, so we're going to say 2 gamma is equal to the length of the margin. All right, and therefore, if we dot this vector, as shown in the blue arrow, with the direction perpendicular to the margin, you'll get a vector that has the length of the margin. Okay. And so if we take this is the direction perpendicular to the margin. So w over the norm of w dotted. So basically, we take the transpose of it and we dot it with x1 minus x2. This will give us the vector, and we want this to be equal to 2 gamma. Okay, so this will be the length of the margin. Okay, when you take the dot product onto the between x1 minus x2 onto this vector, you get the length of the margin, and we're going to just kind of arbitrarily set that to 2 gamma. Okay, so what we're going to do again is we're going to say this is equal to +1, and this value is equal to -1. Okay, so if we let w transpose x1 minus b equal to +1, and w transpose x2 minus b equal to -1, okay, some constant value here, then we can expand this out, right? So if we kind of distribute the w transpose, we're going to get w transpose x1 minus w transpose x2, right? And then what I can do is, because we're taking the difference between these, I can add some constant to this value and add a constant to this value, and it's going to not make a difference, all right? And then we're going to say this value is equal to 1, and we're going to say this value is equal to -1, and so when I combine these, I get 1 plus 1 here, okay? And so that will add up to 2. That will cancel with the 2 on this side, and we're going to basically get the width of the margin. We're going to just say is the norm of vector w. Okay, the distance of the basically the norm of vector w, which is kind of interesting because w is just basically a set of coefficients such that it forms the hyperplane here, or the set of all x's that multiply with w to equal some constant forms this hyperplane here. Okay. And so because the norm of W is in the denominator, what we want, maximizing the distance gamma, is now going to become equivalent to minimizing this norm W. Okay. And so what we want to do is we want to find the W. Okay. We want to find the W that's the smallest W possible. Okay. But the W that we choose still has to satisfy these constraints. Okay. That when I do W transpose X minus B, it's going to be greater than or equal to 1 for all of the positive x's, okay, and then W transpose X minus B is going to be -1, right? -1 or more negative for all of the negative x's, right? So if we look at this picture, here W transpose X minus B is equal to 0. Here it's +1, and then as I go further out, it's going to get to be some value larger, okay? And then as I go further this way, it's going to become some value that's even more negative than -1. So we want whatever W is, it's subject to this constraint, okay? And so a clever way to kind of summarize both of these constraints, okay, is to take the product of the sign, okay, the label being Ti equal to 1 and Ti equal to -1, we can say that Ti multiplied times W transpose Xi minus B, that has to be greater than or equal to +1, okay? So it's obviously true for this, and then when you take it with this and you multiply this value by -1, then that's going to flip the sign and make this positive as well. So so this is kind of a clever way to put both constraints into one equation. Okay, so now we have a constrained optimization problem, all right? And so the what we want to do is we want to minimize this. Okay, we want to minimize this, which will share the same solution if we try to minimize this. Okay, and we try to we're going to do this only because it'll make kind of taking the derivative and solving a little bit easier. And it's subject to this constraint, okay, where the class label multiplied by kind of the value of the kind of your hyperplane vector, or the vector that defines a hyperplane, multiplied by this is greater than or equal to 1, and that has to be the case for every single observation, right? Okay, so optimizing a function subject to a constraint can be achieved using Lagrange multipliers. Okay, I don't know if you guys remember Lagrange multipliers from, when do you guys do that? Is that Math 31B? 32A, okay. So you do it then, okay. So so you do that, and the way you do this is basically you add these terms for every constraint, right? So you so whatever your objective function that is that you're trying to minimize or maximize or whatever it is, okay, you're going to add these additional terms there, so that the optimum of the kind of the new function will correspond to the optimum of the original constrained problem. All right, and so we're going to have n of these Lagrangian terms, okay, and you're going to have one for every single observation, okay, because every single observation has to satisfy this this constraint, okay, and so so the new objective function can be written as this, right? So you're going to get W transpose W, okay, so this this W transpose W is equal to basically the norm squared here, okay, and so we're going to put that in there because this is what we're trying to minimize, and then and this is basically all of the different constraints, okay. We've got the constraint, we've got one for every single observation that we have. Okay, there is math in the textbook, and I opted not to include it. Okay, I mean it can be done, but unfortunately there's no. You can write through this, okay, and you don't get a closed form solution. Okay, there's not a closed form solution to the Lagrange multiplier problem, but it can be apparently you can solve it using quadratic programming, and I never learned quadratic programming, and I tried to look it up, but it was more work than I wanted to learn. So um, so I don't actually know how quadratic programming works. Um, but but apparently it can be solved, and you set it up kind of using these Lagrange multipliers, and apparently the rest you just say, all right, computer, do the quadratic programming for us. Okay, so basically just kind of it will run through like an iterative algorithm to find the solution here. Okay, so what does this mean? Okay, um, we can run this, all right, and basically this is the same data points as we've been having, and this is the boundary that it finds. It gets graphed kind of not nicely, but you're going to get this linear boundary, and this is using there's a SVM function inside this this library E1071. Okay, has a SVM function in its library, and these are the support vectors as we pointed out. Okay, and so here's just I think I mentioned this earlier that you can add or remove points other than the support vectors, and the boundary will not change. Okay, so here I've added more of these things, and as long as these 3 points remain the same, the location of this boundary is not going to change. If you add a point somewhere inside the margin, that's going to drastically change the boundary. So that's not something that you so these 3 points would become the new support vector. Okay. Anyway, the constraint that we used here is that W transpose X minus B has to be greater than or equal to 1. If we take this, okay, and that's going to give you what's known as the hard margin, okay, and again it looks this is the resulting picture, okay. But again, perhaps the hard margin, this maximum margin thing, is not the best result, okay. And so another option is to bring in what we call a soft margin, okay. So the hard margin says this has to be this constraint has to be true, okay, because we're going to say that the closest points are going to be labeled +1 and -1, okay. And then with the soft margin, so we're saying this has to be true, okay. We're going to take this multiplied by a, and we're going to minimize this. With the soft margin, we're going to say, you know what? As long as it's mostly right, we will accept it. Okay. So so sorry, I didn't typeset this. I was trying to get my notes together, and didn't finish in time. Okay. So the hard margin constraint says that the true class label, whether it's plus or minus, and kind of your decision boundary, when you multiply those together, they have to be greater than 1. Okay. And the soft margin will say, you know what, we're not going to require that it has to be at least farther than 1. Okay, we're going to allow things to have a, when we multiply this, the sign of our the label times the boundary, it doesn't have to be greater than 1. It can be greater than basically a number smaller than 1. Okay, and so this is xi sub n. Xi sub n just has to be a value larger than 0. If xi is between 0 and 1, then that's going to allow for points that are between the margin. And then if xi is greater than 1 itself, okay, then let's think about what that means, right? We're going to say, so if xi is between 0 and 1, we're going to just say that Tn times basically, your boundary has to be greater than or equal to some number, I guess, between 0 and 1, okay? And the way we currently have it defined is that the support vectors kind of form the value, the border 1, but what it's going to say is basically you can have a point on the inside, and that will fit the constraint. Okay, so if we bring a point inside, that point inside will not have a distance greater than 1. Okay, this value will be smaller than 1, but it will still fit the constraint. Okay, if this xi term ends up being larger than 1, then it can allow the point to actually even be on the wrong side of the boundary. Okay, so if you have a case like this, okay, you can actually still draw your boundary kind of the way it used to be, and this blue dot will end up on the wrong side of the boundary, okay, but that will still satisfy the constraint. Okay, so as long as it doesn't go too far on the wrong side of the boundary, okay, it will still satisfy this constraint. All right, and so this was known as the soft margin classifier, where your plus or minus b is still defined by these dotted lines that go to some points selected in the data set, but it allows for individual values to end up on the wrong side here. Okay, and so this will be this would be the constraint that we use for the soft margin. Right? I don't know if that completely makes sense here, but basically, with the hard margin, we're saying everything has to be at least greater than or equal to 1, where 1 is the dotted lines, and then here we're saying everything has to be greater than or equal to some arbitrary number that is less than 1. 1 is still the dotted lines, but this allows for points that are between the margins, and also even points that are on the wrong side of the boundary. Okay, and then when you expand this, or when you try to apply this to be the Lagrange multiplier, and I apologize for my terrible handwriting here. What we want is we generally want basically the sum of these xi's to be, or not the sum of the xi's, we'd rather our xi's be quite small, right? So 0 is ideal. If you have xi equal to 0, you're basically getting the hard margin constraint. But then if you allow xi to be greater than 1, you can misclassify a point if it means having kind of other good properties per se regarding kind of the w's that you've chosen. So what you're going to do is you're going to try to figure out kind of what this xi value is for every single observation, and now we're minimizing basically the norm of w plus the sum of the different xi terms. Okay, and it's subject to this, that all of these things, all of the signs have to satisfy this new constraint, this kind of relaxed constraint. Okay, and this is kind of set up in like the regularization problem, in that you've got basically one side, which is basically the W's. You want to minimize this, and at the same time, if you focus only on this, it might cause this to have undesirable traits. And so, so there's some constant C that balances basically between these two objectives. Okay, you're trying to minimize the total of the different X's that you've observed, along with minimizing the norm of W. And it's subject to all of this. Again, this is a you can apply Lagrange multipliers and some kind of quadratic programming for the to search out the different solutions here. Okay, and so there's not a closed form solution, but we apply quadratic programming to search for it. Okay, and when you do that, it will basically find solutions kind of like this when you do it with R, and I'll include some code for how to achieve this. This is just kind of a very brief introduction to the concept of drawing a linear boundary between points that are linearly separable, and obviously this is kind of a constrained, not a constraint, but this is a small scope of the problem. And so on Friday, we're going to look at applying what's called the kernel trick that will allow us to search for boundaries that exist in a that are nonlinear. Okay, but for today, we just introduce kind of drawing a linear boundary and introduce kind of some of these concepts of drawing a margin and also allowing for a soft margin here. Okay, that's all I've got for you today, and yeah, we'll take our midterm on Wednesday, and oh, the quiz answers. No, I don't think I've even created the quiz. Okay, so give me a minute. I still have to actually make the quiz on CCLE. Today, let's see, it's week 7, Monday. We will choose D and A. I guess those are answers I had before, but yeah. D as in dog for the first quiz answer, and then A as in apple for the second quiz answer. So D and A for today's quiz, and just give me a minute to have them made here. Okay, we'll continue the topic of SVM on Friday. Good luck as you guys study for your midterm, and we will see you guys on Wednesday, either at 10 a.m. or 10 p.m. California time, whatever time that is for you in your time zone, but either 10 a.m. or 10 p.m. For the midterm exams. Okay, so D and A for the quiz, and give me a minute, and I'll get those made. All right, thanks guys. We'll see you Wednesday.